Okay, so I'm now recording. So today we're going to hear from Alex Rodriguez, who's finishing undergraduate in our group, doing great work on eccentric nuclear disks and how they can be perturbed by galaxy mergers. And so without further ado, let's hear from Alex.
Great, I'll share my screen. Okay. Okay, yeah, so today we're going to be talking about galactic mergers and eccentric nuclear disks. So this work is based primarily off of our recent paper called Merger-Induced Alignment Within Eccentric Nuclear Disks, authored by me, Alexei Generozov, and Professor Anne-Marie Madigan from our work here at JILA in Colorado. Okay. So we've mentioned the term eccentric disk many times by this point. It would probably be pretty useful to actually define what one is. So this is simply a region within a galactic nucleus with a bunch of stars on apsidally-aligned eccentric orbits around some host supermassive black hole, or SMBH. Now, our nearest galactic neighbor, M31, actually contains two brightness peaks shown in this leftmost image, first described by Lauer et al. In 1993. Now, he showed that these two brightness peaks shown here could actually be explained by the existence of an eccentric disk within M31's center. Furthermore, work has actually shown that these disk configurations are likely present in many other galactic nuclei as well. So, in addition to being within our nearest galactic neighbor, they are also quite prevalent throughout the known local universe. Now, if we turn our attention to these right two images here, we can see a model of what an idealized eccentric disk looks like viewed face on and edge on. Now, before we can jump into the physics of disks in mergers, we first need to understand the work that's already been done on understanding isolated disks. So we base the majority of our discussion here on Madigan et al.'s paper from 2018. And this left image, being figure 1 in that paper, shows a black line, which represents the bulk of the eccentric disk, and also a red line, representing an orbit that has been tugged or torqued ahead of the bulk of the disk. Now, when this happens, the red orbit will be torqued to a higher eccentricity, or inherently a lower angular momentum. And when this happens, it slows down to actually become more aligned with the outer disk. So when this occurs, this means that an eccentricity gradient must develop in order for the disk to still stably precess, where this just means that inner orbits are more eccentric than outer ones, and vice versa. And this effect is shown in this other figure, figure 4 from Madigan et al. In 2018 on the right side. So a useful statistic for characterizing the overall state of a disk is just its overall disk alignment. So naturally, more stable systems will be more aligned and less stable systems will be less aligned. Not really any surprises there. How do we actually usefully define this? So we can do that using the eccentricity vector of an orbit, which is just a vector pointing from apocenter to pericenter with magnitude equal to the orbit's eccentricity. After that, we can project the eccentricity vector into the plane of the orbit, where IE, shown in this left-hand image, just gives the orientation of the projection of the eccentricity vector within the plane of the orbit with respect to the x-axis. Now, by taking the circular standard deviation of this quantity IE for a collection of orbits, we can get a measure of the overall alignment of that disk. So, what does the actual alignment of an isolated disk look like over time? So that's what we have in this right plot here. We can plot the alignment of a disk, which is the standard deviation of IE, sigma IE versus time. And when we do that, we see periodic variations in the strength of disk alignment. And while this result is actually new, we can understand it using the physics that we already know. What we're seeing here is really just the outer disk precesses retrograde, and the inner disk will precess prograde. And when this happens, this just means that when the outer and inner disk are maximally separated, this corresponds to maximum disalignment, say at like 500 orbits, and vice versa, what you see at like 1,000 orbits. Due to these dynamics, eccentric disks are excellent candidates for TDEs, or tidal disruption events. Now, a TDE is simply an event that occurs whenever a passing star passes within some tidal radius of the black hole, where extreme tidal force rips the star apart, causing a bright flare. Now, this image on the left shows a hydro simulation of what this effect may look like. And in an eccentric disk, as orbits may oscillate, this corresponds to oscillations in the orbit's eccentricity. And if the orbit becomes eccentric enough, it can actually pass within the tidal radius, and that's when we get a tidal disruption event. Now, models of these regions in galaxy nuclei at this point have only studied how these disks evolve independently from all their bodies in the universe. An important question is, how realistic is that really? So according to Hopkins and Quadrat simulations from 2010, this assumption does not necessarily accurately model what's often happening in these systems. So they found that these disks can often form in gas-rich galaxy mergers, which implies that a second supermassive black hole can also likely be present in these systems. So that is going to be the main topic of discussion for the remainder of this talk, mainly how a second supermassive black hole affects the dynamics of an eccentric disk. If we turn our attention to the right-hand image, we see what an idealized model of this system might look like in a relatively close-in phase of the spiral of the binary, where the secondary is at a relatively close-in semi-major axis, or end is also on a circular coplanar orbit, which is going to be the fundamental assumption that we make. So now that we've established the relevant background, we can jump into our new simulations of eccentric disks and mergers. So to study these systems, we use n-body simulations using Rebound's IAS15 integration framework for Python and C. And to simulate the disk, we initialize 100 equal mass stars on eccentric orbits with eccentricity of 0.7, where the total disk mass is 5 by 10 to the -3 that of the central object. And we choose these as work has already been done on this exact simulation setup. And we mainly just want to see how our new secondary supermassive black hole affects the setup of the conditions that we already know. So to mimic the galaxy merger, what we do is we fix the secondary on a circular retrograde orbit at the various masses and semi-major axes shown in this table here, where we note that masses of the secondary are normalized to that of the central body, and additionally, the semi-major axes are relative to that of the inner disk edge. We mentioned the fact that the circular retrograde orbit is that the circular orbit of the secondary is retrograde, and we note that in a few slides we return to the issue of the perturber inclination. So yeah, now we can actually get to the science now that we've established all the background and how we set up the simulations. So here we show the results of the previous table, where we plot the overall alignment of the disk, again being the circular standard deviation of IE, sigma IE, for this various set of masses and semi-major axes from that previous table. So there's a lot going on in this plot. We note that the dark regions here are less aligned, correspond to less aligned disks, and light regions in this grid correspond to more aligned disks. We also are fundamentally comparing our results to what an isolated disk looks like. And we have that shown here on the color bar represented by, I believe, yeah. So an isolated disk's alignment corresponds to a circular standard deviation of IE of 65 degrees, which is relatively dark. So what we're seeing here is that actually nearly half of the plot is more aligned than an isolated disk. And most unexpectedly, massive distant bodies have the most drastic effect, peaking with a semi-major axis of 9 and a mass of 5 by 10 to the -1, which is what this red circle you're seeing is here, where here in this case, the disk is 4 times more aligned than an isolated one. And we call this red circle P ideal, in abbreviation for ideal perturber parameters. We will refer to this exact grid point quite significantly for the remainder of this talk. So just remember that P ideal means idealized perturber parameters. And we'll try and make it clear when we're referring to P ideal exactly what we mean. Next, we want to compare the orbit properties of the most drastic point in our previous plot, being P ideal, to that of an isolated disk. So to do that, we plot the eccentricity evolution of these two cases, and we can also actually visualize what these orbits might look like after 500 orbits using an orbit plot. So to help us with that, we first need to define the secular timescale in secular dynamics or orbit average dynamics as just being the characteristic timescale that occurs here. So for us, it is 200 orbits as defined in this topmost equation, where m naught is simply the mass of the central object, and m disk is just the mass of the overall disk. So to see the secular timescale in action, we can plot the eccentricity versus time for both P ideal and an isolated disk, which are the plots shown on the left side here. And we see that the evolution is pretty comparable before 1 secular time, again at 200 orbits, modulo oscillations about the system center of mass for P ideal. After 200 orbits, the isolated disk eccentricity drops off while P ideals actually stays the same. And the reason for that is we're seeing a dampening of secular effects occurring for P ideal. Additionally, in the orbit plots, shifting our attention to the right, we rather expectedly see the results from our previous two plots that P ideal indeed has more eccentric and aligned disks after 500 orbits. So we've previously described in detail how disks will precess in time. What about P ideal? So to see if P ideal precesses or how it precesses, we plot IE versus the semi-major axis of stars in the disk after sufficient secular resolution, or after sufficient secular evolution, which we choose to be 300 orbits. So in the top plot, we can see the effect of how the inner and outer disk precess oppositely, leading to differential precession, shown by the significant axis tilt that we see here. We also interestingly see the effect of that negative eccentricity gradient we described before, where close-in orbits have much higher eccentricity, shown by the much darker color of orbits at close-in semi-major axes. So shifting our attention to the bottom plot for P ideal, we see that P ideal maintains a nearly uniform eccentricity profile for the entire evolution of its orbits. So orbit 300 still has a uniform eccentricity profile, unlike the isolated disk, as it turns out that for P ideal, this eccentricity distribution turns out to be stable against precession. Here, this is just because the perturber adds an extra source of precession, which keeps the disk aligned with time. We can characterize the strength of the eccentricity gradient by just the slope, or DEDA, and we've seen that the slope DEDA is approximately 0 for P ideal. And a natural question is, what about other perturber parameters? If we try and recreate the alignment plot from before of all of these different perturber parameters and how that corresponds to alignment, what do we see for the eccentricity gradient? So again, using the same parameters as before, we actually see that the eccentricity gradient is nearly perfectly correlated to the alignment. This just means that no eccentricity gradient, say for P ideal, corresponds to a highly aligned disk, and vice versa. Now, we remind you that isolated eccentric disks produce lots of TDEs. So what about P ideal? Well, we can detect TDEs in our simulations using rebounds built-in collision we can detect TDEs using rebounds built-in detection capabilities. And if we measure the number of TDEs here, shown by n TDE out of 100 stars, we actually interestingly see that TDE had that P ideal has the fewest TDEs with no TDEs. And again, the overall structure of this plot is similar to now not only the alignment one, but now also the eccentricity gradient one. So this just means that regions with no TDEs also have no eccentricity gradient, and also now have high disk alignment and vice versa. So based off of the IE versus semi-major axis plot, we can posit that we can analytically describe the behavior of what's going on here as related to P ideal, based off of the effect that P ideal bit has on the precession of the disk. Now, the precession rate of the disk is simply the time derivative of IE. And with a perturber, a secondary simply adds an additional source of possible precession to the disk. So the total precession rate of the disk, DIE dt, is simply the contribution from both the disk and the perturber respectively. So how do we estimate each of these contributions? So the disk portion is actually quite simple. We can estimate the disk-induced precession rate just numerically. And the perturber piece is a bit more tricky, but we have to get the perturber-induced precession rate analytically using a spherical harmonic expansion up to quadrupole order, after which we use Gauss's orbital averaging method to get a final expression for the perturber-induced precession rate, which is what this bottom expression is here. So summing the two final contributions, we expect regions where the total precession rate has a slope closer to 0 to correspond to regions of maximal disk alignment. So we test this hypothesis in this top plot here on the left, where indeed for our highest mass perturbers, this correctly predicts the location of P ideal, as it indeed does have the flattest slope relative to these other semi-major axes. So what if we extend this idea to all of our masses? Does this correctly reproduce all of the behavior we see in our alignment plot from the beginning? So it actually does. So that's what we see in this bottom left plot, where we see the correct prediction of the location of P ideal, as well as the overall qualitatively similar behavior between this plot and all of the other ones we've seen so far. So a good question is, does this always work? What assumptions have we made here that might restrict our analysis to just this idealized case? And it turns out that, unfortunately, this formalism does not always work, as this expression here predicts, this expression here referring to the analytic description of the perturber-induced precession rate predicts equal results for prograde and retrograde perturbers. However, if we do simulations of that is actually not what we see. So if we duplicate our old plot of the retrograde perturber orbits, which we've seen, just the one on the right, for prograde ones, we see that there is somewhat of a qualitative difference between these two plots, where most interestingly, we see that the conditions for maximal alignment no longer occur at P ideal, again, being this really white point here over on the right at a mass of 0.5 and some major axis of 9. We now see conditions for maximal alignment have shifted over to the left. So we are clearly missing something in our analytic formalism. And an interesting question is, how do we modify this to understand exactly what's going on here? So we need a new method for getting this perturber-induced precession rate. How do we do this? We can do this using 3-body integrations, using a central black hole, a massless test particle, and a circular perturber with the same conditions that we've been using before. So after we've initialized the 3-body integration, we can measure the average precession rate over 50 orbits, and doing so combined with our old method for getting the disk-induced precession rate numerically, we show what this method gives us in these two plots here, where we indeed see that that the prograde one correctly predicts the locations for maximal disk alignment as being shifted down to lower masses at a semi major axis of 9. So it appears we've solved the problem in a sense. Also, the stitching in the bottom right corner might look a little bit odd, but we note that the sections of the plot in the bottom right are crossed off to simply indicate that these close-in massive perturbers produce highly scattered chaotic orbits, which no longer have a well-defined precession rate based off of our analytic formalism. So in conclusion then, we summarize with retrograde perturbers are better described by this analytic formalism than prograde ones, as non-secular kicks for the prograde orbits are greater due to the relative velocity between the secondary and test particle being smaller. So we have these novel, interesting results. How robust are they? They don't mean anything if they aren't robust in a sense. So as a reminder, we've previously simulated 100 particles in our disks and integrated over 500 orbits. If we extend this to higher particle number disks, say 200 and 400 star ones, and look at the evolution of these disks for long times, how does that change the dynamics that we're seeing at play here? So before we can really jump into that, we first need to define the two-body relaxation. We first need to define two-body relaxation roughly as just being the time required for a star to lose all memory of its initial orbit, which in our simulations approximately scales with the number of particles n. Now that we've done that, we can turn our attention to the plot on the left, where we plot p ideal for these different particle number disks over long times. And what we see is a divergence between these different particle number disks at late times due to artificially strong two-body relaxation because of these higher particle number disks. So we conclude from this plot that we can trust our results at early times, say at 500 orbits, because it's before this this computational constraint has really come into play. So our conclusions are true in a sense. Next, we turn our attention to the right plot. As a reminder, we've only really looked at massive distance secondaries on prograde and retrograde orbits. So what about other inclinations? Because the inclination of the secondary doesn't necessarily have to just be coplanar. So based off of this plot with all of these different inclinations for massive distance secondaries, we see that it's possible for roughly half of all these inclinations to result in disks that are more aligned than that of the isolated one, which are what the red line and black line you're seeing are. Those correspond to the isolated disk. So our findings here are robust in a sense, as it's statistically more probable than not for massive distant bodies to significantly align disks, even if it is not as drastically as the alignment that occurs with p ideal occurring over on the right for perfectly retrograde orbits. So our formalism, future work and complications, our formalism only works, unfortunately, for coplanar perturbers, meaning that we cannot accurately understand this previous plot here of all of these different inclinations based off of our current techniques. Another issue is the lack of dynamical friction between background stars affecting the secondary, as we expect sinking of the secondary with time due to dynamical friction, but our simulations do not account for this. Another issue is the lifetime of the secondary is quite tricky, depending on the geometry of the nucleus, as the lifetime is highly dependent on the geometry of the nucleus, or the secondary may live for much longer depending on it. For example, in a spherical one, a p-ideal like perturber may survive for 10 to the 8 years, giving some context of the timescale that that our findings might be relevant for. And one more issue is, we only considered perturbers on perfectly circular orbits for simplicity. How accurate is this really? So In reality, the eccentricity of the secondary will be excited by stellar encounters from the disk. So even though it's excited by stellar encounters from the disk, it will be dampened by gravitational radiation at close enough semi-major axes. So this implies that the growth of eccentricity from stellar encounters will be relatively low, and in fact goes to 0 for circular orbits, according to Quinlan's work from 1996. However, we would really need to do a much more detailed study of this in the future. So that is the bulk of my talk. Summarizing everything, we found that massive distant secondary supermassive black holes could significantly align eccentric disks. In addition, we found that these regions of parameter space corresponding to high alignment also had no tidal disruption events, a nearly uniform eccentricity profile, and a complete lack of differential precession. Now, to place our results in a bit broader astrophysical context, we do so for M31. So there's been evidence in the past for a recent major merger occurring in M31 a few gigayears ago. And today an eccentricity gradient is observed. And because of this, we could effectively rule out a P ideal-like configuration, as this would disrupt the eccentricity gradient. So yeah, that's pretty much it. Thank you for coming. If you have any detailed questions, feel free to email me here. If you have any other questions, I guess we could do a bit of a Q&A. So.
Nice job.
Yeah, thank you.
Questions for Alex?
Yeah, I have one. Can you guys hear me? Or
Yeah.
Yeah, we
Okay.
can hear you fine.
okay, my green line wasn't flashing at me. So, is the secondary a particle or?
Yeah, we treat the secondary as a particle.
Okay, but it's on a fixed orbit.
Yes, it's on a fixed orbit, but again, we're not considering any dynamical friction.
Yeah.
Friction from the disk effect.
So could you, in theory, just not put it on a fixed orbit? Just let it, just give it, just put yeah, just not fix it on a circular orbit. Is that possible?
So it's fixed in a sense. We've looked at the actual evolution of the orbital elements of the secondary, and it does evolve somewhat in time. We're just saying that it's fixed in the sense that we're not considering any dynamical friction. It's not literally fixed. It's still being somewhat affected by the particles in the disk, although not significantly.
Okay.
Yeah, if I can jump in.
Yeah.
So the issue is that probably there are a lot more right? It's like we're considering the secondary and the disk in a vacuum, right? But there's probably like a whole background nucleus. And like the idea is that if you included that nucleus, the secondary would spiral in. Just from dynamical friction on other background stars that aren't included in our simulations. But the secondary is a live particle in the simulation.
Yeah,
so
maybe
the interaction. Yeah.
Well, can I ask a quick question? I'm wondering, you had mentioned that the analytical model that you had didn't differentiate at all between prograde and retrograde orbits. I was wondering if you had an answer for why that was.
So the reason why that is because the method we're using to get the analytical precession rate is Gauss's orbital averaging method, which basically just smears the perturber out in its orbit. So when you basically just smear the perturber out in its orbit, you lose all information about the inclination. If it's prograde or retrograde, you lose all information about it. But if it's slightly inclined, then you wouldn't.
Okay, yeah.
That makes sense.
Is that the same as considering it as a secular approximation?
Yeah.
Okay. Great, thanks.
All right. Were there any other questions or?
If not, let's give Alex another round of applause, and I'll pause the
Yeah, thank you.
recording. Stop recording.